We study the molecular orbital theory by establishing the various molecular orbitals, their wave functions, with the help of one principle. What is that? LCAO principle. Let us apply LCAO principle to establish molecular orbitals in nitrogen molecule. Let us arrange them in proper energy sequence, distribute the electrons in them, and let us find bond order and magnetic property for nitrogen molecule.
Let us understand the molecular orbital formation in nitrogen molecule, their energetics. I severally said if you want to understand the energy sequence of sigma to pz and pi to px, pi to py, why sigma to pz is of higher in energy than pi to px, pi to py. You go through the one video, that is the making sense for MO diagram for nitrogen molecule. That is the other video. Here I am talking general explanation, in particular symmetry application, symmetry interaction, that I am not discussing in this video. See, nitrogen atomic number is 7. So electronic configuration 1s2, 2s2, 2p3. When two nitrogen atoms will come closer in order to form a molecule, the inner orbital, that's a 1s orbital, will not able to interact with other 1s orbital despite of fulfillment of condition to form molecular orbital. What were the conditions? First, atomic orbital should be of same energy, energy same. Second, they should be of same symmetry, symmetry is same. Third, appreciable overlap. There is no appreciable overlap. Therefore, they remain non-bonding orbitals. Their electron density in atomic orbitals and in molecular orbitals remain same. Whatever the electrons are there in those atomic orbitals, they will be remain. But in molecule, difference will be that 1s orbital electrons which were separately in atom, now this 1s orbital electron belonging to that nucleus but within the molecule. Now let us understand the higher energy levels and the orbitals. 2s orbital of one nitrogen will interact with 2s orbital of other nitrogen. First condition, same energy is fulfilled. Let us find the symmetry for 2s orbital. 2s orbital means is a spherical orbital, has the wave function positive or negative. Along internuclear axis, along z axis, if I consider a line and if I rotate the molecule around that line, if I rotate the 2s orbital around that line, then there will be no change in the phase of the 2s orbital. Positive will remain positive only. It means 2s orbital is symmetric about internuclear axis, symmetric about cylindrical axis. The symmetry term for this is sigma. So 2s orbital is of sigma symmetry and it can interact with the other sigma symmetry orbital, that's the other 2s orbital. So those 2s orbital will interact to produce two molecular orbitals, one bonding which is of low energy and other antibonding which is of high energy. Bonding orbital will be a result due to which kind of interference? Constructive interference, positive interference, addition of wave function. And antibonding orbital will be the result of destructive interference, subtractive interaction. What about the overlap integral? Overlap integral for bonding orbital will be greater than 0. It is positive, means between two nuclei more electron density will be there relative to atomic orbitals. Therefore, the attraction will be more there between the two atoms. Therefore, energy of that molecular orbital will be lower. It is more stable than atomic orbitals. And for antibonding orbital, overlap integral will be less than 0. Means at overlap region, electron density will be less compared to electron density in atomic orbitals. Due to decrease in the number of electrons, due to decrease in the electron density, nuclei can directly face to each other. And because of that repulsion, energy for that antibonding orbital will increase relative to energy of the respective atomic orbitals. So keep in mind, attraction means decrease in energy, stability. Repulsion means increase in energy, instability. Therefore, we say no, lower energy orbit is a bonding orbital. They help for bonding. An antibonding orbital will oppose for bonding. Now we will calculate bond order later on. Let us come to the higher energy orbital. That's a 2p orbitals. Triplet is there, 2px, 2py and 2pz. Their names are enough to explain their orientation. But what are we considering? Z-axis is to our left, right. Y-axis is up and down. And x-axis towards us and away from us. If I consider this convention, when those Two nitrogen atoms are combining along Z axis. So conventionally I am considering Z as a bonding axis, Z as an internuclear axis. Then which orbitals will experience more interaction, strong interaction? Yes, the orbitals which are colliding head on head, and other orbitals will experience lateral interaction. Now let us know which orbitals can collide head on head. Of course, 2pz orbitals. So 2pz orbital symmetry, just find, say this 2pz orbital is along the internuclear axis, along the Z axis, along the bond axis, along the cylindrical axis. And if I rotate that pz orbital around that, then positive lobe will remain to positive side, negative lobe will remain to negative side. What we say for such symmetry? Sigma symmetry. And this sigma symmetric orbital from one nitrogen atom will interact with sigma symmetric orbital of other nitrogen to produce sigma bonding orbital and sigma antibonding orbital. We represent it as sigma star. The energy by which bonding orbital decreases should be more, and energy by which antibonding orbital increases also should be more. But what are we finding in this diagram? The decrease of bonding orbital is less. Increase is appreciably good one. The reason for that is in the atomic number of nitrogen, is in the nuclear charge or nuclear power of nitrogen, is in the energetics of 2s and 2p orbitals. Energy gap between the 2s and 2p orbitals of nitrogen is small, and because of that the energy of 2pz orbital is little higher. Exact reason you will understand if you go through the video, that's the other video, making sense for MO diagram of nitrogen molecule, N2 molecule. But time being, at second year level, if you could able to remember and understand this MO diagram, will do. Now come to the pi interaction. Come to the 2px and 2py orbitals. The 2px and 2py orbital, they are of pi symmetry. Why I am saying? Because they are not symmetric about internuclear axis. Means if I rotate those 2px and 2py orbital around internuclear axis, their wave function will change. Means positive wave function can come to the negative side and negative will come to the positive side. Uniformity, regularity is not there, and such kind of symmetry is a pi symmetry. The symmetry is pi, interaction is lateral, interaction is weak, and that results in the pi bonding. Two kinds of the molecular orbitals, bonding and antibonding. So 2px and 2px will interact to produce pi 2px and pi star 2px. 2py and 2py will interact to produce pi 2py and pi star 2py. Since the energy of 2px and 2py are same, and extent of interaction means overlap. Let it be lateral overlap, but it is equal, it is same. So decrease in energy of bonding orbital, that's a pi 2px and pi 2py, should be same. Means pi 2px and pi 2py should be degenerate of same energy level. By the way, increase in energy of pi star 2px and pi star 2py also should be same. They should be degenerate. By green coloration, their formation is represented. The energy by which bonding orbital decreases, with that much amount of energy, antibonding pi orbital increases. Now let us understand the electronic distribution in the nitrogen molecule. Nitrogen atomic number 7. So nitrogen molecule will be with total 14 electrons. How can we distribute those 14 electrons? That we have to study. For that, energetics should be clear. Energetics is made clear in this MO diagram. But the orbitals, that's the 1s orbitals, those remain non-bonding. Those are not represented. We need to consider them. But 1s is a first orbital, inner orbital, and it is only one orbital in that shell. So by letter, what will the symbol? K. So let me represent K as a symbol for 1s orbital of one nitrogen, and K is a symbol for 1s orbital of other nitrogen. Means in that K, 2 electrons are there in each K shell. So total how many electrons will be there in non-bonding orbitals? 4 electrons. Now after 4, let us see the electron filling. Next higher energy orbital is our bonding orbital, sigma 2s orbital, and it can accommodate 2 electrons. It can help for bonding actually. Other higher orbital, sigma star 2s. it also can accommodate 2 electrons. It opposes for bonding. Means whatever the efforts are done by sigma 2s for bonding, those will be cancelled by sigma star 2s. Next higher energy orbitals, 2 are there, pi to px and pi to py. So now 4 electrons in the kk, 4 electrons in sigma 2s and sigma star 2s. So 8 electrons we have distributed. 9th electron will enter in the pi to px and 10th electron in pi to py. As per which principle? Hertz's rule of maximum multiplicity. 11th electron will enter in pi to px, will pair there. 12th electron will enter in pi to py, will pair there. 13th electron has to find the higher energy orbital. And where is the higher energy orbital? Which is that sigma to pz. 13th electron will be in sigma to pz. 14th electron will pair in sigma to pz. From this, we can find out bond order. What is the formula for bond order? Bond order is equal to number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. Let me calculate the electrons present in the all bonding orbitals and antibonding orbitals. How many electrons are in bonding orbitals? 8. Which are those? 2 in the sigma 2s and 4 in the pi to px, pi to py and 2 in the sigma to pz. So those 8 electrons. How many electrons are there in antibonding orbitals? Only 2. Which orbital it is? Sigma star 2s orbital, in which 2 electrons are there. 8 minus 2 divided by 2. What is the answer? 3. It means 3 bonds are present in the nitrogen molecule. Let us describe these 3 bonds. I said electrons in sigma 2s will help and electrons in sigma star 2s will oppose for bonding. So I don't consider for discussion at this moment. In pi to px and pi to py, 4 electrons are there. And 4 electrons are equivalent to how many bonds? 2 bonds. So it means in nitrogen molecule 2 pi bonds are there. But by the way, in sigma 2 pz 2 electrons are there, and those 2 electrons in sigma 2 pz can be responsible for how many bonds? 1 bond. Yes, means what? 3 bonds are present in the nitrogen molecule. How can we describe those 3 bonds? 1 bond is sigma bond due to 2 electrons in sigma 2 pz, and 2 are pi bonds due to 4 electrons in pi to px and pi to py. Triple bond means due to 1 sigma and 2 pi. Yes, nice explanation for bond order. How many unpaired electrons are there in the nitrogen molecule? In molecular orbitals, in atoms you will find unpaired electrons, but in molecule there is no unpaired electron. Unpaired electrons are 0. If unpaired electron is not there, then what will be the magnetic property? Yes, absolutely right, diamagnetic. N2 molecule is diamagnetic in nature with triple bond between nitrogen atoms. Let us understand the representation of its electronic configuration. See left side, nitrogen molecule N2 is represented, and 3 horizontal line means equivalence. That equivalent to, in special bracket, different orbitals and electrons present in those orbitals are represented. If you find those orbitals by blue-green coloration, I represented non-bonding orbitals. Actually, those shells are there, K and K. I put them in bracket. So combined electrons present in KK I will represent as a superfix, and that is also by green-blue coloration. How many electrons are there? 4 electrons. And remaining molecular orbitals I represented by white color. But electrons in bonding orbitals, maybe sigma bonding orbital or pi bonding orbital, I represented by white color. And electrons in antibonding orbitals by yellow coloration. That may help us to find the bond order. After KK, that's a non-bonding orbitals, next higher energy orbital is a bonding 2s orbital. That's a sigma 2s. It has 2 electrons. Next one, sigma star 2s. It also has 2 electrons. Afterwards, pi to px and pi to py. These 2 different orbitals are there, but both have same energy level. So I say those are degenerate. Each one has 2 electrons, means pi to px2 is equal to pi to py2. Then higher energy orbital, sigma to pz, has 2 electrons. Further higher energy orbital, pi star to px and pi star to py. They are also degenerate. Their energies are same. So in between is equal to sign is represented. And how many electrons they do have? No electrons. And highest energy orbital, that's a sigma star to pz, also has no electrons. And then our special bracket completes. That's the electronic configuration for diatomic nitrogen molecule. It's a homonuclear diatomic molecule. Whatever the explanation I had given to you in this video is a general explanation. Particular perfect explanation is there in making sense for MO diagram of nitrogen molecule. It is a other video. As a homework, simple two questions. Only you have to mention bond order and magnetic property of nitrogen molecule. Already answers are given in this video. Bond order, one number will be there, and magnetic property, paramagnetic or diamagnetic. I am waiting for your answers in comment box.
In general, application of molecular orbital theory to nitrogen molecule you have studied. Let us compare it with valence bond theory. Electronic configuration of nitrogen 1s2, 2s2, 2p3. 300 electrons are there on one nitrogen atom, so 300 electrons on other nitrogen atom, they will overlap to form 3 bonds. Yes, the same explanation is given by molecular orbital theory. What about magnetism? 3 electrons are paired there, so it should be diamagnetic. Same is the explanation for molecular orbital theory. So here, the results of valence bond theory and molecular orbital theory are same, but kind of bond, sigma bond, how many bonds, pi bonds, how many bonds, that how wisely molecular orbital theory has explained, that much wiseness is not there in valence bond theory. That's the importance of molecular orbital theory. Let us understand this molecular orbital theory application for next molecule, that's oxygen molecule.